Welcome back everyone to part 2 of this series on coding regression. Now we just saw there's plenty of issues with linear regression when we're dealing with that sort of curved data set. And we saw two main things arise. One is that just based off a performance metric like mean absolute error or root mean squared error, it's not clear how poorly linear regression is actually fitting to the data. Instead, we had to do two things. One was actually visualize it, and there we could see the straight line. And then two, we could see that all the outputs for our linear regression model looked quite similar in value. Let's see if we can fix the issue with polynomial regression and what limitations we have with polynomial regression. Let's head back to the notebook where we left off. Okay, here I am at the notebook. We left off last time with linear regression, and we noticed it just fit a straight line along the average. So what we want to do now is be able to test out polynomial orders. And in order to do that, I'm going to make a quick helper function, and if you want, you can just copy and paste this function from the lecture notebook, but I'm going to define it here. What I would like is a function called runModel that is going to take in my model, whether it's a linear regression model, a k-nearest neighbors regression model, a random forest regression model, etc. And then it's going to take in xtrain, ytrain, and xtest, ytest. And what I want to do are three things. I want to fit the model to the training data. Then I want to get performance metrics. That way I can compare them. And then I want to plot the results of the model for the signal range. That is at 0 to 100. So let's first do this. We're going to get that model. It's going to be put into the function. And so I'm simply going to say model fit xtrain, ytrain. So note here, I'm not actually passing in a model that's already fitted. I'm passing in something like model equal to linear regression. So once we have the model fit, we're going to get the metrics. And in order to do that, we need to do the following. We're going to say predictions is equal to model.predict. And this is where scikit-learn's uniformity across models makes this sort of function really easy to do. And we're going to predict off xtest. And let's just grab root mean squared. So we're going to say np_sqrt of the mean squared error, pass in ytest against those predictions, and then I'm going to print out using f-string literal formatting. We're going to say root mean squared error, and then I'm simply going to put in or pass in root mean squared error. So upon running this, right now I'm going to fit the model, and then I'm going to get some metrics, and I'm going to report back root mean squared error. Let's go ahead and also report back mean absolute error. So I'll say mean absolute error is equal to mean absolute error, ytest, and then predictions here. And then we're simply going to say print MAE, and then pass in MAE. Okay, so next after that, I'm going to plot the results on the signal range. So a lot of the code we just did already. We're going to say signal range is equal to np_arrange 0 to 100. And then I'm going to say the output of this is equal to what we did last time, where I take the model, I predict, and then I have to resize the signal range to be reshaped from -1 to 1. And then I'm just actually going to copy and paste the code that we have up here, which is create a figure, create the scatter plot, and then plot your predictions. So I'm going to copy this, come back down here, paste it in. Let's get the indentation right. I'm going to create my figure, going to create my scatter plot of the original data. To avoid confusion, we can make this a different color. I can say comma color, and you can make this red or black, doesn't really matter. I'm just going to make it black. The reason I do that is so that it's easier to see the blue line created from PLT plot here. So we have signal range, and then I actually call this output instead of signal predictions. So let's call this signal predictions here instead. Okay, so that's going to create our plot, which means now I can have this helper function where I simply pass in my untrained model, xtrain, ytrain, xtest, and ytest, which are actually already defined, and I should get a bunch of output out. So let's actually copy this line, run this cell to define the model, and then I'm going to paste this in here, and right above this, I'm going to say model is equal to an instance of linear regression. Run this, and you should see the results. You should see mean absolute error, root mean squared error. It was trained inside this model, and then it was also tested inside this model, and we have the final plot out here. So let's create a pipeline to test out polynomial orders, which will be great for us. So I'm going to come back here, and let's comment out this run model line and start setting ourselves up with a pipeline for polynomial orders. And the reason it's going to be a pipeline is, recall, for polynomial orders, we actually use sklearn's pre-processing to create polynomial features. So let's go through the steps. We say from sklearn.pipeline import make pipeline. And then for this particular case, I will say from sklearn preprocessing import polynomial features. Okay, so I have those two things going. Let me make a couple more cells here. And what I want to do is, recall, make pipeline is actually a pretty simple command. We say pipe is equal to make pipeline, and then we simply pass in the steps we want to perform on the incoming data set. And for that, it's going to be 2 steps in a row. First, we're going to transform xtrain or xtest into a polynomial features data set where you define what degree of polynomial we want. In this case, let's start off with degree is equal to 2. Then the next step we're going to do is a linear regression model. And this is how we can use pipeline with a polynomial regression. Previously, we saw this just done in 2 steps, but this has it all in one easy to use model, and this pipe is going to act like a model that can directly run here inside run model. So we run this, and pipe has everything you would expect a normal model to have. So we can call fit on this, or fit predict, fit transform, depending on what the actual steps in the pipeline are. And then once it's fitted, you should actually be able to call it predict. So I'm going to delete those, and instead I'm going to uncomment out run model, and instead of model, I will simply pass in this pipe object, which will create a polynomial feature set off of xtrain, and then train it with a linear regression. So this is polynomial regression in 1 step with the pipeline. Go ahead and hit run model, and then we should see that 2nd degree polynomial curve. And now this is a great example for you to play around with for the bias variance trade-off. This is the sort of situation you have to be extremely careful about when interpreting your performance metrics, because as you get to higher and higher levels for this polynomial, so let's go ahead and do degree, let's say up to 10, and if you were to run this again, take a look at my mean absolute error at 0.22. If I run this again, notice my mean absolute error has been almost cut in half to 0.12. But now I'm going to start picking up on a lot more variance here. So notice that as we get to more and more extreme degrees, I will end up getting or picking up more and more noise. And for this sort of data set, if I knew my signal was always going to be between 0 and 100, I could probably find some polynomial order that was able to balance this out. And we talked a lot about this in the polynomial lecture series, where we showed you how you could plot out error and then decide when you reached a high enough degree of polynomial features. So you can keep running this. It looks like 3 degrees is not enough, so you could go to something like 6. Check that out. And it looks like a 6 degree polynomial is actually fitting this data quite well. And it doesn't seem to be overfitting to the training set. So that's actually performing quite well. But keep in mind, we could do something extreme, like a 50 degree, well, let's not do 50, that's probably too crazy. Let's do 25 degrees, run that, and you would get to something that's overfitting way too much to the training data. You can see that here. And suddenly your mean absolute error on your test data is going to start skyrocketing. So we already talked about the bias variance trade-off back in the polynomial features lecture. So if any of this is confusing to you, go ahead and review those lectures. We talked about this sort of degree and trying to find the correct degree. But you can see if you go too high of a degree, you start picking up way too much of that noise. So in general, if we knew that our signal was always going to be between 0 and 100, we could be satisfied with degree 6. But what if you want to expand this to a signal range beyond 100, but you don't have any data points for that, and you don't know what to expect or how well this is going to fit? That's where you probably want to go to a more robust model. Something like k-nearest neighbors regression or decision tree regression, support vector regression, etc. So now what we're going to do is, throughout the next lecture series, is we're going to have this run model just so we can compare the different fits and errors of a variety of different types of models, and just to visualize how they're actually fitting to the data. We can quite clearly see here that a polynomial regression is going to have these curves, and it's going to get kind of noisier and noisier as you go to higher degrees. Let's see just how much noise is picked up for some other model types. And we'll do that all with this run model function that we created here. Okay, I will see you in the next lecture where we explore many other models.